All right. Welcome back. Hopefully you had a good long weekend. Does anybody have any questions before we get started? Is there anyone who didn't sign up for the paper presentation yet?
No, I had a question.
Yeah.
Because the sign-up form said groups of 4 are possible.
Mm-hmm.
I think so it said groups.
Yeah. So 3 is desired. I mean, if you really have like 4 people already lined up, you can put 4. But what I said is like, given that we have around 20 papers and around 60 people, so it would be 3. But since it's slightly more than probably some of the groups can be 4. So that's why, like, when you're signing up, you can put 4. I'm gonna probably assign the papers sometime tonight or tomorrow, so you're gonna hopefully see it tomorrow. Any other questions? All right, so if you remember last time we were discussing, we started talking about cryptography, specifically encryption and decryption, and specifically, we started talking about perfect secrecy and symmetric encryption, right? And if you remember, I told you that what we want to achieve is something like this, which we call it perfect secrecy. And kind of like a semi-formal definition of this is that if we have any 2 messages and we encrypt them using any possible key, it will result in 2 different very random ciphertexts. If you look at these ciphertexts, we shouldn't be able to tell which one is coming from which message. So essentially, the probability of distinguishing between 2 ciphertexts and saying that which one is for which message should be exactly equal. Okay. If we have that, we say that we have perfect secrecy. Okay. The question becomes is that can we achieve perfect secrecy? And the answer to that was yes, we can achieve perfect secrecy. And then in order to achieve that, we can use a very, very simple crypto system where essentially all we need to do is just XORing the key with the message. And if we can do that, there are proof, actually not very trivial proof, that this is indeed perfectly secret. The caveat though is just like tiny little things that we are putting here, and that is the size of the message and the size of the key should be exactly the same. If even 1 bit less, then there are proof that you're not going to achieve perfect secrecy. Okay. I also explained like how the encryption and decryption works, and I told you that encryption and decryption is technically just XORing the message or the ciphertext with the key. And since this is a symmetric encryption, then both for the encryption and decryption use exactly the same key. So we last thing that we tried to discuss last time was issues about one-time pad, OTP, and how we can fix this, obviously, right? The biggest challenge with OTP is that the size of the message and the key should be the same, which means that this is basically not practical. There was also the second issue with one-time pad, and that's when we are trying to use the same one-time pad with the same key multiple times, which we call two-time pad or many-time pad. And what I said there was, if I have the same message and have the same key, if I XOR this many times, I'm gonna get exactly the same ciphertext each time. As a result, if you remember, I told you that in perfect secrecy, what you want to do is that by seeing the ciphertext, you shouldn't be able to tell anything about the message. But this obviously is not really kind of following that, because, for example, if I have many yeses and very small amount of no's, I can basically see how many times I see the ciphertext, a specific ciphertext, and then I'm going to say that if I know the distribution of a message, I can map that into distribution of my ciphertext and essentially can tell which one is which. So as a result, it's not achieving perfect secrecy for many-time pad. So one thing I want you to notice is that one-time pad is only perfectly secret if you only do it one time. Okay, that's why the name one-time pad. It's not many time pad. So many time pad is not perfectly secret. Okay. And the kind of I gave you a hint here that in order to achieve this kind of perfect secrecy, we cannot have a deterministic approach for encryption, because for a deterministic function, if you send the same input, you will get the same output, right? It's basic mathematics. So you need to kind of like randomize this process somehow within that function, such that if you send the same input, you get a different output, right? That's what you want to achieve in a crypto system. But of course, this randomness should be predictable on the other side as well, because we should be able to decrypt the messages as well. If I cannot decrypt, then there's no point of doing any encryption, right? Okay, so let's talk about these two problems, the problem of the size and the problem of many time pad, and let's focus on the first one, the size, okay? So in order to achieve a practical crypto system, we need to kind of like relax a little bit assumptions in perfect secrecy, okay? So how do we relax it? We're gonna relax it by this, that if you remember that I told you that, okay, if I have all the messages and all the, all the encryptions, like different encryption or ciphertext, there should be 0% difference in terms of probability of message 0 and the encrypted version of message 0 versus the encrypted version of message 1. Okay. So the way I'm going to relax this is I'll say that, okay, maybe this is not 0, but maybe it's like a very, very small number, which we call it epsilon. Okay. And this is the definition of what we call semantic security, which is actually a very important topic. And that is essentially kind of, again, like not really formal, but it's kind of more high level definition of this is that given two messages and their encryption, then the chance that the attacker finds out which encryption is for which message should be smaller than epsilon. Okay. And how small is this epsilon? Like, what is this negligible? It's not 0, it's negligible. So there's like a huge difference between the two. So the negligible is usually very, very small number. Okay. This is kind of like, we use it as what we call a security parameter. Okay. So if you pay attention to kind of these different encryption systems, you'll see that they usually come with what we call security parameters. And these security parameters kind of also decide what this negligible is. To give you an idea, we're usually talking about 1 over 2 to the power of 128 or 1 over 2 to the power of 256, these kind of numbers. And these are very, 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 very small numbers. We are talking about billions, like 10 to the power of minus, 50 or so. So we're talking about like, billions and billions of numbers, right? So it's very, very, very small numbers. Okay. And then there are proof that, for example, if like we use this number, what is the likelihood of the attacker can, for example, find this information? And usually this will lead into some form of, it will take years for the adversary to really learn something useful from this crypto system. Okay. I'm not going to really like drive the logic again and the proof, but usually if this epsilon is smaller enough, then the attacker really doesn't, it learns a little bit, but that's very, very small that it takes a lot of time for the attacker to really find something useful from the system. Okay. And of course, this number is kind of relative to the power of the attacker and the computational power of the attacker. If you remember, like first week, I told you that one of the biggest things that we need to consider is the computational power and capabilities of the attacker. So when I say, for example, it will take years for an adversary, I'm talking about a bounded adversary or like a normal system. If, for example, the adversary managed to have a significantly faster computer systems that we don't have, in this time, then this number will change. And as a result, we need to kind of make this epsilon even smaller. In fact, actually, like many of the crypto systems used to be smaller sizes, but now they're much bigger. So for example, AES used to be 128, but now 256 is listed minimum. You cannot really go be smaller than 256. All right. So what this semantic security will give us, like what this changing from 0 to epsilon will give us, there is again proof for this, but you just have to take my word for it. that semantic security essentially give us you can use OTP, one-time pad, with a key much smaller than the size of the message, and you can achieve semantic security. Okay, so the importance of this epsilon is that there is an algorithm and there are proof that tells you that you can use one-time pad with a key much smaller than the size of the message, that if you apply that key to the message in the right way that I'm going to describe very soon, you're going to achieve semantic security. And then, as I said, semantic security there are proofs that, for example, if you choose the epsilon certain amount, the attacker cannot really break your crypto system within some time bound. Okay, so kind of two-step thing. Right? So semantic security will give you a one-time pad with smaller key, and then there is another proof that shows you that with semantic security, your system is indeed secure. Okay? So how do we actually kind of like actually do the one-time pad when the key is much smaller than the message? We need to have what we call like a stretching algorithm in some sense. Because, for example, your message, let's say, is 256-bit. And I told you that in one-time pad, I need 256-bit of the key, right? And I told you that I don't like this because this means that there is a 100% over. But now I'm telling you that maybe I can have only 8-bit. I'm just making up numbers. They're not like official numbers. Maybe I can have 8-bit of a key, of a true random key. And the way I'm going to do it is I'm going to still do one-time pad, which, if you remember, it was like basically XORing M and key. So I'm going to still, do that. But pay attention to the size difference, right? You cannot XOR an 8-bit to a 256-bit, right? So we first stretch this into like something like key prime. So we make this 8-bit with some algorithm that I'm going to describe very soon to a 256-bit. Then I'm going to apply XORing or one-time padding with the message. Okay. So one-time pad with semantic security is a two-step approach where you first stretch the key and then apply the key similar way as if the side of the key and the side of the message was. Okay. Another way, and I'm gonna very soon explain how this stretching will work, so don't worry about that for a minute. Another way to think about semantic security is kind of like a weaker model of semantic security is what we call message recovery attack. And essentially the message recovery attack tells you this, that if I have very a set of messages, okay, and then this is like a limited set of messages, and then I'm just randomly pick a message from this set and encrypt it and send it to a challenger. The challenger is basically the adversary, and ask the challenger that which message do you think I encrypted? Out of these m different messages, which one did I encrypt? The probability that the attacker can easily detect this should be kind of 1/m plus some epsilon. Okay, so it's not exactly 1/m, but it's 1/m plus something. So it's slightly better than 1/m. Okay, and then you can see that how if I have a very large message and very small epsilon, how this basically becomes almost zero. Right, so this is how our systems become a secure system. Does that make sense? So, for example, let's say my messages are 256 bits of message, right? So the size of the M is 2 to the power of 256, huge size. And this epsilon is also very small, maybe 1/2 to the power of 256. In other words, I'm telling you that the chance that the adversary knows which message is this is very small number. Okay? And then, of course, how the attacker can increase their chances by seeing repetitive instances, right? So if I see this more often, the probability of the success rate of the attacker becomes larger and larger. But since this is a very small number, then if I repeat this millions and millions of the time, I still have a very small number. So this is how we kind of like prove that this indeed is a secure system. Yeah.
So epsilon is the upper bound on the probability of the attacker guessing.
Yes, so the question is epsilon is upper bound. Yes. So as you can see, it's basically the probability is less than equal than epsilon.
Oh,
So at best is epsilon. All right. And as I said, there are proof that shows that with semantic security, we can get that. By the way, if you're interested in kind of like any of these proofs, various ways that you can do, you can learn about this. One is I'm going to actually show you a reference book for this. I'm going to post it on Campus Wire. The second thing is that you should just Google these. You will find these are very, very established, concepts. There's like usually a nice Wikipedia page for each of these things. Okay. Okay. So now that we kind of talk about a general message saying that, okay, there is message 1 or message 2, there's also another question that we need to kind of answer, and that is individual bits within message. Because, for example, I told you that let's, for example, assume that your message is 256. Okay. And when I say I cannot distinguish between one message and another message, means that I cannot predict all the 256 bits. Okay. But what if about the first bit? Maybe I can tell whether this is an even number or an odd number. Maybe I can tell whether the most significant bit is 0 or most significant bit is 1, right? So what about individual bits? And in fact, semantic security is also going to prove that not only you cannot tell the difference between messages as a whole, you should not be able to do the same thing for even individual bits, okay? In other words, I cannot tell whether the bits 0 of the message was 0 or 1 with the chance better than 1/2 plus some epsilon, right? So essentially random, right? Or the first 4 bits should be 1/2 to the power of 4 plus some epsilon. Okay. So in other words, the adversary has no better detection chance than random plus some epsilon. And again, this epsilon is so small that you can kind of neglect it and assume that this is random. Okay. And there are again proof that shows that how individual bits, like how the whole message reduced to individual bits and so on and so forth. That again, if you're interested, you can read about it. Okay. So now that we kind of know that what we are going after, what do we need? Now the question is, how do we actually build this semantically secure system? And the main thing that we need to do is I need a mechanism for that stretching, if you remember that, because I said that, okay, we start with like a small seed that we can generate from some random random number generator. But I need to find a mechanism that, for example, if I have 1 megabyte of data, I can stretch this key to any arbitrary size that I want. Okay. If I have this capability, then there you go. I'm good with building the system. Okay. So we need some form of stretching mechanism. And the typical way of this stretching mechanism is using what we call a stream cipher. Stream cipher is only one way of doing this. Later on, we're going to talk about block ciphers, which is actually more popular and much more efficient. But stream cipher is kind of like one way of stretching your keys. Okay. And remember that not any stretching is secure. So you cannot have an ad hoc and arbitrary stretching mechanism say, okay, look, I have my random key. I stretch it by, I don't know, by kind of copying multiple times. Here you go. This is the stretch version. This is a secure system. Just very, very careful that your stretching should follow specific rules that I'm going to describe. And if it does, then it's a secure system. Otherwise, ad hoc mechanisms or not. Generally, remember this, that for cryptography, it's a very, very bad idea to kind of come up with your own functions and ad hoc methods in order to achieve security. It usually has to follow very, very rigorous process. And even many of these algorithms that follow these, rigorous processes, they ended up being not secure. So for example, there was this very famous kind of stream cipher called RC4, which has been used for a very long time. But after several years, somebody managed to found to find a particular vulnerability in the systems, and it's no longer being used because it's no longer secure. So just very, very careful and be very hesitant in using anything but the standards that commercial off-the-shelf systems are using. Anyway, so let's actually talk about stream ciphers, and let me give you a semi formal definition of a stream cipher. So we can define a stream cipher as something like this. Consider S as a vector of size L, lowercase l, and this is a binary vector, okay, zeros and ones of size L. Okay, and now assume that your message and your ciphertext is also a binary vector of size uppercase or capital L. And of course, as I told you, that the size of the key, the initial seed, is much, much smaller than the size of the L. That's the whole point of achieving this. Okay, so our stream cipher, our stream cipher or ciphertext in general, a crypto system. For encryption of S and M, we're going to have this function G, or this generator function, that takes S and generates a new key prime, and then XOR that with M, and then you will notice that the size of the G of S is essentially L, okay? The size of the message, okay? So what the generator function does is that takes a smaller input, which we call seed or secret, stretch it to the size of the M, and XOR it with the M, okay? And then similar things happen for the decryption, exactly similar as to one-time pad, if you remember. So in this part is exactly one-time pad. The only thing that is different is that what used to be K is now G of S, okay? And then the main thing for G of S is that it should be very, very hard for the adversary to distinguish between G of S and the actual truly random number, which used to be the key that I told you, right? Remember that when I was defining perfect secrecy, I said that key has to be truly random. What we want to be able to achieve is that G of S should be very, very close to random. It cannot be truly random, but it should be very, very close to random. So the probability of distinguishing between G of S and the random number should be epsilon. And if that's achievable, then we see that this is a secure stream cipher system. Okay. We usually call this G of S a pseudo-random generator, or PRG. Okay. So it's not truly random because you cannot achieve a truly random in a function. But it's a pseudo-random function that's as close as possible to a true random generator. Okay, so G of S is usually a PRG, and then of course the question becomes, how do I build a PRG, right? And as I said, we don't do ad hoc. There's actually lots of engineering going on with how do we build PRGs. Okay, so as I said, a secure stream cipher or a secure PRG should follow a standard series of tests. Usually this is like if you, for example, say that, oh, I found a new PRG that is secure. So you claim that this is secure. There are standards. Usually the National Institute of Standards has a series of standards that you have to follow that in order to show that your random number generator is truly a secure PRG. Okay, this is mostly a statistical test, like the distribution of individual bits, the entire system, and so on and so forth. Again, if you're interested, you can go and check it out. To give you some examples of popular stream ciphers, these days the most popular one is Salsa and Cha-Cha. And as I said, the one that used to be very, very popular before was RC4, which no longer is used because it's no longer a true random generator, like, a pseudo-random function, a secure pseudo-random function. I definitely recommend you to, for example, Google Salsa stream cipher, and you will see how it works. Okay. Any questions from stream ciphers? I'm not going to provide additional details of any of these, but again, if you're interested, definitely go and read about them. Like, how do we actually build such a stream cipher? Okay, so if you remember, I told you that there are two big problems with one-time pad. The first one was the problem of the size, and now we fixed this problem, right? Because now we have a pseudo-random generator, PRG, that takes much smaller key size and stretch it and make it like a random looking number. And now you can actually XOR it as you would in a one-time pad system. Okay. But there's still the second problem, which is if I do the same thing, I'm not gonna get a different results. Even if I use G of S, as long as my S and my M is the same, since G of S is a deterministic function, XOR of G of S and M is also a deterministic function. For any similar S and M, I'm gonna get the same outcome, right? So I have this problem of many time pad or at the very least 2-time pad is not a secure system, right? So what should we do? Any suggestions? What do you think we should do? There's like a very simple thing we can do, yeah.
Change the key.
Change the S, right? So if I change S, feed it to G of S, and that will create a different results. What do you think is the problem of that? What's the issue with changing it? Yeah,
Takes a long time
it takes a long time to what?
to generate a key and then like re-verify.
Yeah, but it takes it's again a feasibility issue. It's better than what it used to be, but again, think about this: is that every time I want to send a yes, I need to figure out a way to exchange another key with my receiver, right? And if I can't exchange a key secretly, I might as well send a message with that, right? There's no point of, oh, okay, I want to send you a message. Let's actually have another kind of interaction to send you the key. And now let's send. Or you can say that, okay, maybe I can do one time and send you 100 different keys, right? So you have 100 different keys, I have 100 different keys. And then we're gonna send messages, but we are limited, right? We can only do 100 different messages. We cannot go beyond, right? So two feasibility issues. Either I need to kind of like do this on demand, which is painful process, or I can do it at the first time, but that means that there's only a limited number of messages I can send. Okay. So how do we go about this? We go about this by using what we call a nonce and a single a kind of a source of randomness to achieve this process. Okay. So the idea of a nonce, and generally the idea that we're going to go after, is that instead of having a deterministic ciphertext or a crypto system, we're going to have a probabilistic crypto system. Okay, and we usually call this if you remember, I told you that this means that we are secure against chosen plaintext attacks, which means that even if the attacker can choose their plaintext, our system does not still leak anything. Okay, so how do we do that? We're going to use this thing called nonce. Okay, which means that it's a number that is only used once. Okay, that's kind of how we call this. That's why we call it nonce. So the nonce is another input to the stream cipher. Okay, and all it needs to do is all it does is essentially adding randomness to the system, because as the name suggests, we use every different value only once. The second time that we want to encrypt a message, we change the number. The third time we change the number, and so on. So we never have the same message and the same nonce ever. It's only one time. Okay. And with this, we can actually now achieve what we want to achieve. Again, since the stream cipher is specifically, I'm not going to describe how the stream ciphers work. You're not going to see how the nonce is going to be used, but once I'm describing AES and generally block ciphers, you will see the impact of the nonce. But in other words, when my G of S is no longer G of S, it's actually G of S and N. Okay, and as a result, I don't change this, but I change this. So I get K1 for N1, and then I'm going to get K2 for N2, and so on and so forth. And this way, I'm guaranteeing that every time I change the nonce, then I'm going to get the different values. So you might ask, okay, how does this different than sending different keys? Because the nonce does not need to be secure, okay? The only thing that nonce needs to be kind of like the same for the sender and receiver is that they need to be synchronized, which means that they have to agree on what is the initial value of the nonce when they start, and then after that they can just increment it. Okay, so if I want to send 100 messages, for example, I start with n is equal to, I don't know, like 5. The first time is 5, then 6, then 7, then 8, then 9, all the way to 105. Okay, and why this is secure? Because knowing nonce does not give anything to the adversary. Okay, because still S is not known, and there are proof that if S is not known, they cannot reverse engineer and reverse this process. Okay, so that's why we have a secure crypto system that you can kind of not infinite, but as long as your nonce is, for example, if your nonce itself is 256, then I can send 200 to the power of 256 different messages to the receiver, and that's more than enough for my entire life, right? And the next time I can always kind of synchronize my nonce first and then continue from there. Okay, I'm going to come back to this nonce once we actually describe the block cipher, so you're going to see it in action as well. Any questions about stream cipher? So one thing I want you to kind of pay attention here is that this part is basically one-time pad. Okay, so this is still XORing the message with a key, but the way that we're creating this key is that we start with like a fixed key, which is much, much smaller. And this is really the secret part of this entire crypto system. So this is the secret key that if the adversary knows this, the entire system will break. But other than this, everything else about the system is completely known, including the nonce. The only thing that for this system to work is that the transmitter and receiver needs to know and agree on the same key. They also need to synchronize their nonces. So if they synchronize that, then they're good to go. Okay. So that's pretty much it with kind of the encryption system that we're using. Okay. With this, we're happy. We have kind of achieved everything we wanted to achieve. Okay. But there is more to this, to the crypto systems, especially for symmetric keys, and that's the story of block ciphers. Okay, the reason that we're really not using stream ciphers and we are kind of using more block ciphers is that we rarely kind of do streaming. Okay, we usually kind of do things in blocks, right? You send a message and your message is, for example, 256-bit or 512 bits and so on and so forth. So things are kind of like in block level. Okay, so usually, I mean, in fact, this is just the way that kind of the field has grown over the years, is that a block-based approach where I take one block and encrypt it and then go to another block and encrypt it was proven to be much faster and much more efficient than if I do it kind of bit by bit. Okay. There is no specific reason for this. You could have, and we could have found other methods that does the streaming faster, but it's just, it was more intuitive in the field to use block ciphers rather than stream ciphers. Okay, so I just wanted to say that there's no like significant difference between stream ciphers and block ciphers, but the community kind of like decided that block ciphers is going to be much more efficient, and that's why these days we mainly just use block ciphers when you're using encryption. So when you're saying that there is this symmetric key encryption mechanism, we're talking about the block cipher or blocking based encryption mechanism, not a streaming based. Okay, so what is a block based approach? So what's the difference? Okay, so this is the idea of what we call block cipher. Okay, and it's very, very different than stream ciphers and one-time path. Okay, and to give you an idea, block cipher is the biggest example of block ciphers is AES. Okay, the Rindle algorithm. So that's why you probably haven't heard about cha-cha or salsa. I mean, other than the actual dance, but like block ciphers of like stream ciphers with cha-cha or salsa, but you definitely have heard about AES, right? And that's kind of like, kind of testament that why block ciphers is being used very, very much. Okay. So how do we actually build block ciphers? It's slightly different than the way that we build stream ciphers. Stream cipher is mainly based on using one-time pad. Block cipher is very different concept. Okay, so in order to understand that, you have to first, I need to explain some of the mathematical kind of basic blocks first. The first thing is what we call a PRP, or pseudo-random permutations. Okay, remember that we had something called pseudo-random generators. This is a different version, and this one is kind of like, you know, the kind of more mathematical definition of pseudo-random function. Permutation is that if I have a function from domain X, okay, a pseudo-random permutation is a function that maps this function to its own domain. Okay, it's essentially a permutation, right? So it just shifts things around, and it's maps it's one of its own data, one of its own members to another member of its own. Okay. Okay. In other words, if I have you know, a function like this, that I have this different, you know, inputs, a pseudo-random permutation is essentially kind of maps this into some other elements of this this function. So for example, if I have 0, 1, 2, 3, then f of like 0, for example, is 1, f of 1 is 2, f of, let's say, 2 is 3, and then f of 3 is 0. Okay, they could be also mapped to each other, but essentially it's just a permutation. We just move things. Okay, and then one thing we could do is that we can have a keyed permutation, which means that I can define an fk of x or fkx, which essentially is that the fk of x, or if I want to kind of put it in terms of encryption and decryption, if I call it ekp, what it does is kind of like take the key and take the input, and based on some kind of function within that I'm going to describe, it's going to map it to one of its own members. Okay, so a vector of size, you know, k, a vector of size n, and then the output, of course, has to be n as well, because the input and output same size. Okay, so what's the point and what's the importance of a PRP? Is that similar to a g of s, a generator function, a pseudo-random function should be indistinguishable from a random permutation. As in, I shouldn't be able to say that which element is going to be mapped to which element. If I just randomly assign them, it should be any function that I'm going to use for doing this permutation should be pretty much the same. Again, we're talking about semantic security here, which means that I'm not going to get truly random, but the probability I can distinguish between a truly random permutation versus the permutation done by the PRP should be almost the same. Okay. So how do we use PRP? So first of all, PRP, as I said, is just permuting or mapping a function to its own domain. So the idea of PRP for encryption is pretty simple. You take a block, you use a PRP in order to generate a new permutation, a new mapping, and you can call that your encryption. Then you move to another block, you repeat this process, you do it all the way to the end of your message, and you're good to go. Okay? There are few details that I need to describe, but kind of at very high level, this is kind of how the block cipher works. Okay, so really all I need to have is a good PRP. If I can't find a PRP, that's all I need to do. There's no need for a stretching. There's no need for anything like, you know, anything other than that. It's just I do the mapping, and boom, there you go. We have our encryption mechanics. Okay, any questions so far?
If you don't need stretching, how does the key need to be the same size as the message?
So the question is, if I don't need stretching, why the key? So first of all, I'm not using the key for, I'm just using the key in order to decide the permutation. Okay. So here, if you see that in definition, the size of the key is k, but the size of the input and output is n. So n and k are not the same. Okay. So it's kind of like similar to the seed kind of idea that we had, that you can start with, like you are good with even much smaller key.
Okay.
Right? Okay. And then the question becomes, is this semantically secure or is this like perfectly secure? And there are lots of details a little bit of details that I'm going to describe later, and there are lots of proofs that I'm going to skip. But if we have proper randomization and chaining between blocks, so it's not just like these blocks are completely independent from each other. The blocks are kind of relevant to each other. So if I follow a true, like a secure PRP and follow a specific format for chaining, then there are proof that shows that this is semantically secure. And then if it's semantically secure, it goes back to all the things that we already discussed, that's kind of message recovery, single bits, and all those things. So everything I said so far applies when we say something is semantically secure. Okay? And then essentially, if you think about this this permutation function, you should think about this is that it should be very hard to find a new mapping, right? But it should be very, very hard to find the inverse of that mapping, right? So this is what you want to achieve in a true, a good encryption system. That if you give me something, I can quickly tell you that if I know the key, this is the mapping that you're looking for. And then for the adversary side of you, if the adversary does not know what the key is, they don't have any idea what the mapping is, because the mapping is just truly mapping, permutation, right? So this is kind of like very, very high level idea. And of course, the decryption and encryption should be, canceling each other out, which means that if I decrypt an encryption, I should get the message back. So how do we actually build PRP, and what are the PRPs that we are using? As I said, AES is the most famous type of PRPs that we are using in our everyday life. There's another one called DES, and then there's triple DES that is also still being used, but AES is, of course, by far the ones that's being used a lot. The way that we are building these PRPs, similar to PRGs, is that there's no like hard theory or mathematical functions that we follow. There's more of like a combination of some theoretical analysis and some engineering. And that's why I said be very, very hesitant of kind of creating your own PRP or PRGs. You have to follow standards. For example, the story of AES was like there was a big call of we want to create this new PRP, and then a whole bunch of people kind of like, submitted their designs. We went through a very, very rigorous process of multiple years of testing, and eventually this Rindle algorithm, which later becomes, the standard AES, becomes the kind of the commercial off-the-shelf or standard encryption algorithm. Okay, there is no guarantee that we're never gonna find an attack to AES. We might, but at least so far nobody were able to build, break an AES system, at least not a known attack. Okay, so how does AES works? We can have a quick break and then come back and I'm going to describe how AES works. All right, so let's talk a little bit about AES. So I skipped a stream cipher, but and told you that if you're interested, definitely take a look. But let me give you a little bit background on block ciphers. Of course, AES is only one block cipher. There's also many other block ciphers too. But the only reason that I'm kind of talking about AES is kind of it's popular. So how does AES works? So AES works like this, that we typically kind of like have we take a block, and this block for AES is usually kind of like a 4x4 matrix. Okay, that you can think about this as kind of individual bytes, and this is essentially what we call X, or the input. Okay, this is one block, and then we feed this into this machine, which we call AES. Okay. Within AES, we usually have multiple rounds, okay? We have round 1 to round N. There are different versions of AES that has different rounds, like 10, 12, 14. And what we do is that we repeat the same thing over and over in these rounds. So every round is essentially the same thing, but we just repeat it multiple times. The reason for me repeating is that you can think about it to create just more randomness. And then if we do it enough, then we have enough randomness that we are happy. There's usually the final round is slightly different, so we don't do all the things that we do in other rounds in the final round. So there's like a tiny bit of difference in final round versus the others. But other than that, we just do the same thing over and over again, like usually 10 to 14 times. Okay. Each round has its own key, and you can think about the key as a thing that's divided into pieces. Okay. And then each part of the key goes into each round. So we repeat this process with different keys. We don't do it with the same key. We use it with different keys. Okay. How do we create this key? We usually don't have like a large key. We kind of borrow the same idea in stream ciphers, which we start with a smaller key and we use the generator function to expand the key. Okay, but you could have technically do it with bigger keys as well. The way that we expand the key is not the same way that we do it with stream ciphers. Of course, you can use stream ciphers technically here, but we're going to use something else that we call pseudo-random functions in order to expand the keys. I'm going to talk about this after I explain how the AES itself is working. Okay, but for now, assume that if I have n rounds, I have n different keys, which we usually call it round key. The round key goes into this E function, this encryption function. The first input is divided into a vector of 4 by 4, goes inside this E function. I'm going to show you what's going on within each of these. Then the output of this becomes the input of next one. And we repeat this process, but this time with a different key, and we repeat this over and over until we get to our final answer. And there was just a tiny bit of difference in the final round. Okay, so the steps. There is a key expansion. That's the first thing that we do in AES, that we take this key and we expand it to create these round keys. Okay, the good thing about this key expansion is that it can be a parameterizable function, which means that if I want 10 rounds, I can create 10 keys. If I want 14 rounds, I can have 14 different keys. Then I'm going to have the first step, the first initial step, and which what we usually call the initial round key addition, which we usually use it as like add round key. And what we do is that we typically kind of like we XOR bitwise the input with the key. Okay, that's usually the first thing that we do at the initial phase. Okay, then what we do is that we're going to repeat the process multiple times. As I said, we usually either do AES 10 rounds, 12 rounds, or 14 rounds. As a result, we repeat this step number 3, 9, 11, and 13. And as I said, there's like a final round that's slightly different. Okay, so what happens here? There are kind of 3 things that we do, and then of course at the end we do the same thing that I said before, the add round key. Okay, so in the initial phase we just do the XOR of the key and the data. That's it. Then we start this E process that I said. There are 3 things that we do. We call it sub-bytes, shift rows, and mixed columns. Okay. To kind of give you an idea, let me actually show you the picture. This is kind of like what is going to happen on the data. So this is your data. The sub-byte is essentially kind of subbing the bytes, as the name suggests. The shift row shift the rows together, and the mixed column is kind of mixing the columns. So we kind of change individual bytes. Then we change the individual individual rows, and then we mix some of the columns, and then eventually we're going to XOR it with the key, and then that would be the output of the system. Okay, so essentially what we are trying to do, remember, is that we are trying to create some random permutation, right? So we want to kind of mix these things as much as we can in order to achieve what we want to achieve. Okay, so going back to it, this is kind of the visualization to kind of get some idea of what's going on. You can actually follow this kind of like lines to see not everything is necessarily moved all the time. So when we are, for example, mixing columns, we're not necessarily moving all the columns, or we're not necessarily moving all the rows. So if you go back, the sub-bytes is kind of this nonlinear process because we only kind of move things in a nonlinear fashion. And nonlinearity is very, very important because if your crypto system is only linear operations, is reversible. As a result, it's not a secure, crypto system. It's very important to introduce non-linearity to your system if you want to have a secure encryption crypto system. Okay. Well, so with some rules, we're gonna basically substitute a byte with another byte. This is usually there is a table that tells you that, for example, byte number 1 should be substituted with byte number 3. Okay, there is like a predeterministic and predefined table for this. Okay, so that's the sub-byte phase. Then we're gonna have the shift row phase, which the last 3 rows are going to be shifted in cyclically in certain number of manners. So one of them 3 times, one of them 2 times, one of them 1. Okay, and then mixed column is again a linear mixing of good columns, which each column is kind of moved to another column with specific rules. Okay, and these rules are fixed. Okay, it's not changing over time. So all of the AES, they're doing it exactly at the same time. And finally, there's this add round key, which essentially bitwise, we're gonna XOR the key to individual bytes. Okay. And then we repeat this 9 times, 11 times, or 13 times until the last round. The last round, the only difference is that we do sub bytes, we did shift row, and we do add round key. So the only thing that we don't do is the mixed column. So in the last round, we don't do the mixed column. Okay. And there are again proof for why you don't need mixed column in the last round. If you're interested, I definitely recommend you to go and read about this. But eventually that would result in what we call the AES, which is this kind of like mixtures. You can think about it as a glorified way of mixing things that creates some form of a randomness. And we repeat this in order to have enough mixing. Think about this as like a shuffling cards, that you do this enough that you feel like, okay, I have enough randomness in my system. Okay? Questions? Yeah. Quite a good question. If you know the algorithm, why cannot reverse engineer this? Okay. So in order to reverse engineer this, you start from here, right? The first thing you need to do is that you need to reverse engineer this XOR. Without the key, you have no idea what this is. Okay. So here you have no idea where this is. Okay, and then since I do this multiple times, you never can go back previous step without knowing the key. That's really the goal. Yes, if I didn't have this part that involves the key, then sure, you can just go back. And also remember that this is a nonlinear operation, right? So it's not like I can assign, apply a reversible function, because nonlinear function is necessarily not reversible. It's more of like a guessing game that you can do. Without the key, you could have done it, but with the key, you cannot.
How does the receiver also know, like, for example, the lookup tables?
So the question is how the receiver knows what this process is. This process is known to everybody. Okay. So again, this is not something that's the transmitter and receiver agrees.
Okay.
It's always the same. So always you sub byte like byte 1 and 4. That's
Okay.
always in any system. Question is, how is the decryption? The decryption is exactly the same. You just follow the same path. All right, so I need to answer 3 questions to kind of complete this. The first is, how do we do the key expansion? The second question is, what happens if you have more than one block? Do we just repeat this process for every block? Or if you remember, I told you there's kind of like some chaining that is involved. And the third question is, do you think with this process, if I encrypt the same block over and over, do I get the same results or not? Who wants to answer this? Like with what I just explained, if I encrypt yes, do I get the same ciphertext anytime that I do yes?
Yes.
So there is no nonce, or there is no change of the key. So the answer is always going to get the same ciphertext. So I have the same problem of many time pad in something like AES2. So I need to introduce randomness. So I need to kind of use similar tricks that we use for stream ciphers here. And I'm going to show you how we actually introduce that nonce in a second. Okay. So how the expansion works. Of course, you can use your pseudo-random generators to expand. But if you remember I told you, I don't really like pseudo-random generators because they're slow, they're stream-based. I really like something that is block-based. That is kind of like I take a block and I generate another block. So what I would do is that instead of using PRGs, I'm going to use PRF, okay, pseudo-random functions. And pseudo-random functions are actually very, very helpful things because once I describe what is RSA, you're going to see that we're going to still use pseudo-random functions. So pseudo-random functions is very, very similar to pseudo-random permutations or PRP. The only difference is that instead of mapping the function to its own, it's mapping the function to another domain. So if you remember, PRP was X to X. PRF is X to Y, okay? So it's no longer a permutation, it's a new mapping to another function, okay? The big thing about PRF is that you can use a keyed version. So essentially, the key can tell you where this is mapped to and what is that map, okay? So how can I use PRF? I can essentially use PRF this way, that think about your G of S. Instead of S, let's call it K. So all you need to do is that having the, if I have this PRF, I can use the key with different inputs. And then essentially what I'm gonna have is the generator function of that, right? So each of these will generate a different output, and these are my session keys that I can have, right? So I have the same key with different x's. I can generate that x. Let's say, for example, x is a counter 0, 1, 2, 3, 4, 5. For example, I need 10 of these. I start with 0 and then 1 and all the way to the 9. I use the same key k. I use the PRF function. Each one will generate a new mapping for me. That's the key that I'm going to use for that session key, and that's how I'm going to use it to do the generation. Okay. Later on, I'm going to show you another use case for PRF when I'm talking about the RSA algorithm. But PRF essentially can be used as a PRG, right? It's kind of like a very, very sophisticated things, but it's being used for much less strong things. But you can use it. Okay. The reason that I like PRFs and not PRGs is that we know good PRFs that are very, very fast. Okay, but we don't know many PRGs that are that fast. That's the only reason. Efficiency. Okay. So that's the first question, that AES using a specific PRF in order to expand it. We usually call it the AES function. The second question is, how do I encrypt multiple blocks? What do you think? Should I use the exact same format, or if I need to use something else, what do you think we should do? Any suggestions? So let's say, for example, I have two, let's say my system, as I told you, is like 4 by 4 bytes. Like it takes a 4 by 4, 8 times 8, 64, bits of data, feeds it into, let's say, an AES, or 128, for example, and feed it to an AES. If I have 256, two of these blocks, how do you think we should encrypt this? Yeah, you want to say?
Yeah, the next block should be somehow dependent on the previous block.
Okay, so the next block should be somehow dependent on the previous block. The reason for this is there was actually this attack that they showed that if I just do AES separately on the blocks, what will happen is that you're not going to have enough randomness in your entire design. So although that these pixels are not these pixels, but the general shape of sorry about that. The general shape of your system remains the same, because essentially kind of applying the same amount of randomness to every pixel. And if I do that, my shape remains the same, right? This image after what we call the electric code book or ECB type encryption is going to be the same. Versus if I had used another type of kind of randomness that kind of like, change the amount of randomness that I do, and it's kind of make it completely independent from different blocks, then I should get something like this, and this is the desirable, right? So you want your encryption of this image becomes this rather than this, right? So in order to do that and create this what we call diffusion kind of property of encryption, we need to use different methods. The one that I'm going to describe here is what we call a CTR mode, okay? But there's a whole bunch of others like CBC and so on. There are a whole bunch of different ways that you can create this diffusion. The CTR one is like very intuitive. That's why I'm explaining it. So think about the CTR mode as like the algorithm is the following, okay? So my encryption algorithm, which is like K and M, is that we're first gonna split the message into blocks, okay? Let's say, for example, M can be divided into R blocks, okay? So I'm going to split the message into R blocks. And one thing to remember is that if, for example, it's not it's not divisible by R, I need to kind of pad the last part of the message so that to make it like divisible. So for now, let's assume that it's actually exact, copy of R. And then so I'm going to have R different splits of the message. These are my blocks. Okay, these are 64 or 128 bits of data. Okay. Then what I'm going to do is that I'm going to use what we call the initialization vector or IV. You can think about IV as the nonce as well. So the same thing. Then what I'm going to do is that I'm going to assign IV to C0. So this is the first block of my ciphertext. My first block of ciphertext is this random IV that I created. Okay. Then what I'm going to do is that I'm going to basically iterate through these blocks one by one from 1 to R, okay? Each time what I'm going to do is that I'm going to XOR IV and I, so I is the iterator, and then I'm going to encrypt this using the session key of that round. Sorry, not round, using the same key. And then within this is basically a 10 round, for example, AS, okay? So this E is the same E that I described you before. Itself is kind of 10 round, 12 round, or 14. And this is what we're going to get as the partial encryption or PI. Then I'm going to XOR the PI with the message, and I'm going to get my ciphertext. And then I'm going to repeat this ciphertext. To give you the picture, this is basically what it does, okay? So this is my counter. This is the initial counter. I'm gonna, as you remember here, I'm gonna use the key in order to encrypt this. Let me see. So I'm going to first, IV plus the I. I'm going to encrypt this, right? So the first time I is equal to 0, so I'm going to take the IV and I'm going to encrypt this. Then I'm going to XOR it with the plain text, and that would be my ciphertext. Okay. Then for the next block, I'm going to increase the counter by 1. So it would be the IV plus the counter. I'm going to encrypt that. I'm going to then XOR it with the new block, and that would be my second ciphertext. I'm going to repeat that. Essentially, what happens is that what used to be the plain text goes into the key, and then we get the ciphertext, is now I'm essentially just encrypting the nonce plus the counter, encrypt that, and then I XOR that with my message. Okay? And this is the way I'm going to get my ciphertext. And as I told you, I'm going to send this as my C0. So what I'm not showing here is the C0. So this is C1, this is C2, this is C3, and so on and so forth. Okay. And my C0 is essentially the counter, the nonce itself. Does that make sense? Yeah. So the question is, when you're transmitting everything because you are sending a large message, you need to send every ciphertext. But the way that we are creating this ciphertext is not, we are not doing M1 encrypted C1, M2 encrypted C2. And instead, what we do is that we create an IV, okay? We add it with a counter, we encrypt this, then we XOR it with the message, and then we send this. That's the idea. And then if I want to send a very, very large message, all I need to do is just incrementing the count. And then how does the decryption works? The decryption basically works the same way, that you start with the nonce and the counter, you encrypt it using AES, then you XOR it with the ciphertext this time, and you will get the plaintext, because essentially the XOR of the XOR will get you the message. Okay, and all you need to do between the encryption and decryption is this, that I need to know what is the nonce, and as I told you, I'm basically sending the nonce. The second thing I need to know is that the counters are synchronized, so they start from a specific number. It could be 0, it could be 1, it could be any number, but they should start at the same number. And then finally, we should know the same key, that in order, otherwise the encryption won't.
So the dependency that we're creating is just because of the counter? Or
It's because of the counter and the nonce.
the nonce changes as well?
No. So you have a nonce. Yeah, because of the counter, you can play it.
Oh,
Yeah. So in other words, you don't want dependency per se. You want diffusion. You want to create different amount of randomness to different blocks, right? And what happens is that when I'm doing this, one single counter will create a very, very different message and very, very different ciphertext. So what happens here is that even if I'm just changing one bit effectively, the ciphertext will be very, very different, okay? Because these are just random permutations, right? So what I'm getting here, which is the P here and the P here, are very, very different. Then even though that I'm kind of having the same message here and here, this is both of them, let's say, are yeses or nos. I'm XORing them with very, very different things. As a result, this one and this one looks very, very different. That's how it's kind of like created the different.
So the counter always resets to 0.
So the question is, the counter always reset to 0. Doesn't matter what the initial value of the counter is. It just has to be synchronized among the receiver and sender. I mean, it makes sense since it's a counter to start from 0, but it doesn't have to. Because what really matters is the counter plus nonce. And then as you can see, for example, nonce here is just sort of like look very, very random. And by the way, usually there are standards for how you choose a nonce. It's not like, oh, I can choose any nonce that I want. There are standards of like what's the best nonce to use and so on and so forth. All right, so some notes. So the initialization vector, the reason I call it IV and not necessarily nonce is that you can think about it as kind of like combination of a counter and a nonce. Okay, so these together is called IV, but in effect, it's a nonce plus the counter. The biggest thing is that you should never ever use the same nonce twice. Okay, if you do, then the entire thing breaks, because then you will see the exact same message twice, and now you can run frequency analysis on the system. So the security of this system is anchored on the fact that I'm using nonce only once. Okay, so essentially at best we can encrypt the size of the nonce, right? So that's why you probably want to have a big nonce such that you can encrypt many different messages, which is not a big problem. And as I said, that if the last block is less than n bits, we pad it with zeros. We add zeros in the end to make it an r bit, size of a block. Okay, so for example, if you're working on 128 blocks, and then if the last part of your message is like only 10 bits, you add enough bits so that this becomes 128 bits. Okay.
Wouldn't that allow the attacker to know how the encryption is working, because it's just an XOR, right? And it's just being XORed with 0.
It's not just an XOR, right? Because you have a nonce and you have a counter, and then you use the key to get this value. You don't know this P, right? If you know this P, yes. You don't know the P, you don't know the message. You don't know either of them. You just see the eventual results of the XOR.
Okay.
So you don't know whether this was zero. Remember I told you that we cannot detect single different bits using semantic security? That's where. So I cannot tell whether this was all zeros or all ones or some zeros or some ones. If I can tell the difference even for a single bit, then I can break this encryption system.
Okay.
And this is enough randomness that if you do all zeros or all ones, they look exactly random. They look very similar to each other.
Okay.
One thing I want to, yeah.
So do you change the nonce between every message or between every block of the message?
So you don't change none. So the question is, do you change nonce between every message? No, you just change the counter, right? So the counter changes, the nonce stay the same. Your IV changes as a result because IV is nonce plus counter. So the nonce is just one thing that you send. We usually change it over sessions, which means that the next time, like we create a session with the user, we send as many as messages that we want. We close the session. When we start a new session, then we change the nonce. All these questions of how do we send the key, how do we send the nonce, how do we generate the nonce? If you remember, we were talking about primitives, which means that we're talking about kind of the basic blocks. The protocol goes on top of this. And the protocol is the one that decides, oh, how do we even store nonce? How do we know that we have used the nonce once? How do we send the key? And all those things. These are all protocol levels. So for example, TLS or SSH, they are protocols that kind of take care of all these kind of details. Okay. At their heart, they're just this. Okay. They're just AES, CTR, for example. Okay. There's other ways. So for example, there's CBC, there's a whole bunch of others. One thing to remember is that never use ECB because it's not secure. All the others are okay. If you want, there's a very nice Wikipedia page of different modes of AES. There are also nice pictures like this. I think I actually borrowed this from Wikipedia. All of them are there, so you can actually take a look. All right, so how do we do more than one block? The last thing, how do we add randomness? I already explained this, right? By adding this nonce, I also add randomness to the system, right? So the next time I'm encrypting the same message, by changing the nonce, I'm guaranteeing that the output will be different. And as far as the nonce are kind of, synchronized between the sender and receiver, we're good to go. Okay? So I kind of also answered the last questions. All right, so any questions, final questions about symmetric keys? Yeah.
You mentioned that nonce is a number used only once.
Uh-huh.
Is it like used only once, but it's used throughout the session, or is it used once for each message?
No, so the question is about nonce and how it's being used. So when we're creating a session, we generate one nonce, okay? And then we generate counters on top of that nonce, okay? So if I want to send messages over and over again, I just increment the counter and move forward, okay? Once I'm done with that session, I'm starting a new session, then I create a new nonce and then start the counter from zero.
Okay, so throughout one session, the nonce is fixed.
Yes.
Okay.
Any other questions? Symmetric? All right, so let's talk about asymmetric encryption. There are two main questions that you want to wonder: why and how, right? The why part is very obvious. The reason that you don't want symmetric, you want asymmetric versus symmetric, is that asymmetric does not require the same key. Okay, you just use a public key for encryption, and you use a private key for decryption. Okay. As a result, things becomes much simpler because many people can send you whatever messages that they want. They don't need to know your key. All they need to know is your public key, and you can always announce that public key openly to everyone. So public key is not a secret information. The secret key is the secret information. Okay. So the nice thing about this is that if you want to send a message to someone, you encrypt it and send it to them because you are the one who initiating this, and you use their public key. But the nice thing about asymmetric is that it is guaranteed that only the person who has the secret key can decrypt this message. Nobody else, including you who has the public key, can know anything about this message. Okay, so it makes the actual communication much easier because remember this, that if I knew a method to communicate to someone, I might as well send a message through that means, right? Since I don't have any way to communicate to someone and I need to initiate this contact, the very first time at least, there is no way that I can send a key to them, right? The very first time, asymmetric would be a very, very good idea, right? Because I just look them up and see what is their public key. I'm going to send a message to them and say that, okay, this is the secret thing that I want to send you. And then afterwards, I can maybe use that secret thing that I send them as the key between us and then move forward with the symmetric, right? So in fact, there is like this hybrid encryption mechanism that the first time, in order to send the key, you use asymmetric, and for the rest of the communication, you use asymmetric, okay? So what are the differences? I already discussed this. There's no need to agree on the same key. It has the same correctness properties. So decryption of an encryption should result in the same message, obviously. It has the same security guarantees, which means that we are kind of shooting for semantic security here. The only difference is that we need a little bit stronger security guarantees in asymmetric systems because everybody can encrypt. So instead of like having what we call a chosen plain text attacks, we need to be secure against what we call chosen ciphertext attacks, or CCA. The difference between them is that if you remember in symmetric key, in order to encrypt and decrypt, you need to have the key. So it's not like the attacker can choose arbitrary ciphertext. They can only choose arbitrary plain text, okay? But in asymmetric, now the adversary can choose their arbitrary ciphertext and they know the corresponding message with this, right? So what this chosen ciphertext basically tells you is that if the attacker knows a finite set of M and CIs, and by the way, they can easily create this because they have the key, still they should not be able to tell the secret key and they should not be able to decrypt an unknown message. This is what we call a chosen ciphertext attacks, or CCA secure. In asymmetric, we want to achieve this, which is a slightly more stronger than chosen plaintext attacks. Okay. So in order to build a public key encryption, or when I say public key, I mean asymmetric. So from now on, I'm just going to call it public key encryption system. What do we need? We need this magic function, which we call trapdoor function, that essentially it should be easy to compute a function, but it should be very, very hard to invert it, right? And you can easily now understand why, because it should be easy to compute it because this becomes my encryption mechanism, but it should be very hard to invert it because that's my decryption mechanism. The easy thing, the reason that this is a trapdoor function is that I can invert it if I have the secret information, right? So I know the way to escape this if I know the secret. If I don't know the secret, I cannot decrypt, okay? If I can't find this trapdoor function, then I can have an asymmetric, a secure and asymmetric or public key encryption mechanism, okay? And that's kind of like what we're gonna do. So to give you a little bit more more formal definition, a trapdoor function T, an ideal trapdoor function T, is actually a set of three different functions. Okay, it's usually defined over X and Y. So X is the input domain, Y is the output domain, and there are triple algorithms G, F, and I in a trapdoor function. Okay, so G is a probabilistic function that generates the key by randomly sampling it from some domain, okay? So essentially what G does is it creates your secret key and public key from a random domain. So it samples from a random domain, it gives you two numbers, one is the public key, one is the secret key, okay? Then F is your forward path, okay, is your kind of encryption, quote unquote. It's a deterministic function that you give public key an X and it gives you Y, okay? And then I is also a deterministic function that you take Y and secret key and it gives you X, okay? And then of course this has to be one-to-one function. In other words, it should be a pseudo-random permutation in some sense. Otherwise this won't work, okay? So what we need to do, if you think about this even further, is f effectively has to become a one-way function. If I can invert f, I can find x, right? So what I really want to do is that with pk, I can evaluate it in one direction, but with pk, I cannot evaluate it on the other direction. Only with sk, I can evaluate it on this other direction, which is the I function. Okay? So how do we actually do this? What are the good trapdoor functions? And that's where kind of like big, findings in like big advancements in cryptography field has been created. And the biggest one is what we call RSA. RSA names after three main very prominent researchers. And the hardness of their problem is based on factorization problem. We're going to explain how RSA works. So essentially, RSA is this trapdoor function that has these properties that I just described. But there's also other trapdoor functions like Diffie-Hellman, which is based on discrete logarithm algorithms. And there are like some others that you probably have heard of, such as elliptic curve problem, ECC, and so on and so forth. So there are a bunch of different ones that people use. Okay. So what is this RSA encryption like trapdoor function? Okay, so let's actually go with an example. Okay, so let's say that we have Alice and Bob, and this is very common to use terminology to use in encryption mechanisms. Alice is the receiver, Bob is the sender. So Alice use RSA trapdoor functions to create the pair of keys for herself, the PK and SK. Okay, then Alice is going to advertise openly her public key. All right, and the Bob is the sender, knows about this public key. Okay, then what Bob does is Bob going to use RSA trapdoor forward function F in order to encrypt the message. Okay, so Bob and everybody else knows F. Bob knows PK. They have the message, so they calculate this. Okay. Then they send it over the air to Alice. Alice use SK because she's the only one who has knowledge to SK. It's going to use the inverse RSA trapdoor function, and they can decrypt the message. And then the major thing here is that nobody but Alice knows what SK is, and there is proof that without knowing SK, F is not reversible. Okay. So that's kind of like how this works. There are a few important considerations. The message has to be uniformly distributed. The encryption should also have the same many time path property that I said before. It has to be probabilistic. And there should be the message size should be long enough for this system to be secure. Okay. As a result, we're not usually going to use, let me see, yes. We're not usually going to use directly RSA trapdoor functions for encryption. We just use it as kind of like, basic method, and we build something around it, okay? The way we're going to do this, actually, yes. The way we're going to do this is this method called key encapsulation method. Let me see how much time. Okay, we have a little bit of time. Let's have like 2-minute break because we might. This is heavy stuff, so I want to go a little bit, slower. Have 2-minute breaks and then we're gonna continue. All right. So I know my RSA trapdoor function, but I need these kind of properties. I need to make sure that the message is uniformly distributed. I need that to make sure that encryption is randomized. I also need to know that to ensure that my message is long enough. Okay, that's why I don't use RSA trapdoor function directly in order to encrypt things, because it's hard to actually achieve these properties with that. What I do instead is usually kind of what we call a key encapsulation mechanism. What's that idea? The idea is this, that what I'm going to do is that I'm gonna use the public key, okay, to encrypt a key, okay. Then so basically I'm gonna use this public key encryption mechanism to encrypt the key. Then I'm going to use this key from now on to send my message, okay. And the difference here is that I'm gonna encrypt this key using a public key. I'm gonna get the ciphertext, assuming that the receiver can decrypt this. Essentially, the receiver now knows the key. Now I'm gonna the second time I'm really actually sending the actual message, I'm gonna use the actual key that I sent the first time for the encryption, and then I have the C prime. The receiver knows key and knows C prime can decrypt this using key and get the message. Okay. The beauty of this is that this message then can be anything. This key is the random and long size that I want, so I'm gonna get all those kind of properties that I want. This would be my public key encryption mechanism. This is my regular symmetric, like regular AES. So this is my, for example, RSA. This is going to be my AES, and then from now on, I'm going to just use AES. Question.
Yeah, because the sender is using the public key to encrypt their key, does that mean everyone else knows their key?
So the question is, no. So if you remember, when you encrypt things, like public key encryption mechanism says that you have a key or like a message, and then you have your public key. I'm going to encrypt this. I'm going to get ciphertext. Okay. Everybody will see C. Okay. But nobody can decrypt unless they have secret key. Okay. So the whole point of asymmetric is everybody will see C, but they know nothing or learn nothing about the actual message. Okay. So this is what we call a key encapsulation mechanism, or a KEM, okay? So the idea is essentially this, okay? I'm gonna use this three-step approach that I kind of described for a trapdoor function. And I'm not, as you can see, I'm kind of use a trapdoor function, but not directly as E. E is kind of like has the trapdoor function embedded inside it, okay? So here's how I'm gonna do. If you remember, the first thing that we do is that we're gonna use the generator function. For example, the RSA generator function in order to create a pair of keys, okay? Public and private, or secret and public, okay? I'm going to announce this public to everybody, but nobody knows about the SK, the secret, okay? Now, the encryption mechanism works as follows. The encryption mechanism takes PK and message and does this kind of mini steps with it. So the first thing it does is that instead of using the message directly, it's create this random variable X, which is kind of randomly sampled from a domain X. The nice thing about X is that it can be long enough and it's random, okay? The two things that we want from a message. Then what I'm going to do is that I'm going to use the RSA trapdoor function to encrypt X, not message, okay? I'm going to encrypt X using the public key, and that's what I'm going to get as Y, okay? The second thing I'm going to do is that in order to create the key, again, I'm not going to use the message. I'm not going to use the provided key. I'm going to use the X, and I'm going to create a randomized hash function of that. Later on, I'm going to describe what a hash function is, but just think about a mapping of X, okay? And this would be my key. This would be my key, because the key is also, we want to make sure it's long enough and it's random enough, okay? So now I have my key. Now I have my message. Then what I'm going to do is I'm going to encrypt this symmetrically using AES or some other symmetric algorithm. Using the key, I'm going to encrypt the message, and that would be my cipher, okay? Then what I'm going to send is I'm going to send Y and I'm going to send C, okay? This C has the message embedded in it. This Y has the key embedded in it, okay? So these are the two things that the receiver wants. So how does the receiver extract the key and the message? The receiver gonna does this, okay? The receiver knows the secret key and knows Y and knows C, okay? So the receiver gonna use the I function, the F inverse or I function, using the secret key and Y, and this way they can actually achieve X. Okay. Then they're gonna use the hash function, and this hash function is just a publicly known in order to get K, because remember hash of X was K. Okay. So now I have K and I have C. I'm gonna use K and C in order to get my M. And I'm gonna output M, and boom, that's what I want. Okay. And this part, by the way, is true. Okay. So this is what we call a key encapsulation mechanism, because I'm effectively using a public key encryption mechanisms. As you can see, in none of these processes, I never ever use an encryption. Like I never actually communicated the keys. The only thing I used was the public key that's publicly available. But what I really did here was somehow creating some key and using encryption, like symmetric encryption mechanism to really encrypt. And the nice thing about this is that I don't need to worry about the size of the message. I don't need to worry about the distribution or randomness of the message or anything like that. Everything I generated myself. Okay? Any questions? Yeah.
That time we need to be where are those things?
Say it again.
So when you're encrypting, right, ES of K, and that time we need to be, for the otherwise the ciphertext would be not probably this.
This.
Yes.
So the question here is that how do we make sure that this is probabilistic? Here I'm actually generating key on the fly. So the trick is not, I don't really use nonce here. What I'm doing is that if you can see here, each time that I want to encrypt, I basically kind of use a different key. All right.
We will still need to have that process, right? Expand the key.
Yeah, the process is well, yes and no. I mean, depending on what this ES is. Yes, if ES is, for example, AS, then yeah, itself is expanding the key and all those things. Sure. But then what you can do afterwards at this point is I no longer need to do this, keep repeating this cam. I just use a regular ES because now I have the key. Now I can like create a nonce and all those like tricks, right? So at this point, the sender and receiver knows a symmetric key and they agreed on the symmetric key. From now on, I can just use a regular symmetric key. Yeah, so this f of x is basically the RSA trapdoor function. This f inverse of this is the RSA inverse trapdoor function. So what are those functions? Very quickly, I might actually let these you guys to just read this, and then the next time if you have questions you can ask me. So the g of s is basically a random function that creates two prime numbers. Okay. So remember I told you that we need an SK and PK. The G of S in RSA is choose two prime numbers that are large enough. Okay, usually it has to be around 1,000 bits. Okay, find two prime numbers that are bigger than 1,000 bits, very large prime numbers. Okay, call one of them P, one of them Q, one of them becomes your secret key, one of them becomes your public key. Okay. Then you're gonna calculate P times Q, and we call this N. And what we're gonna have is that, you know, this is just like some mathematical theory. If you're familiar with the unit function, the phi function, phi of N is all the prime factor cofactors of a number, and if this is if it's the product of the prime numbers, the co-prime numbers are basically P minus 1, Q minus 1. If you don't have any idea of what is a phi and what is a co-prime, that's totally fine. It's just a mathematical definition. Okay. And by the way, this class from next lecture not going to have any other mathematical functions. So if you care about mathematical functions, this is your last chance. So phi of n is basically defined as P minus 1, Q minus 1, because n is a product of two prime numbers. If you're curious about this, just go and Google what's the Euler torsion function, like what is phi of n, what's the use case of that, and all those things. For prime numbers, another thing that is important is that phi of a prime number is p minus 1. Essentially, all the numbers less than equal of p are the co-prime of that, because nothing is divisible as prime number. That's the definition, right? So this is important things that we're going to use. That phi of p is p minus 1. Okay, and that's kind of the reason that this phi of n is q minus 1 p minus 1, because you can use this phi is qp, and then phi of q is q minus 1, phi of p is p minus 1. That's how we actually got this number. Okay, anyway, so we have this g of s, and then we have this n, and you're gonna later see why this phi of n is important. Then what we're gonna do is that we're gonna choose two integers e and d, and this e and d is gonna be choose such that e times d modulo phi of n is 1. Okay, so phi of n is a number, is a big number. We're going to find e times d such that they're basically modulo 1. So you can think about this as e of d is kind of equal to phi n plus 1. This is how we're going to find e and d. Okay, just two numbers. For example, let's say e is 3, then we're going to find d such that if do minus 1 ed divided by phi of n, we get number 1. Okay, this is how we're gonna find. So usually we fix one and find the other. Okay, that's kind of like what we do. Okay, then we're gonna say that my public key is n and e. Okay, so it's a pair, and my secret key in n and d. In other words, my public key is really E and my secret key is really D. Okay, this is really what we do. So the big thing here is that by knowing E, I shouldn't be able to tell D. Okay, and the big thing about the RSA trapdoor function is that there are guarantees that if I know N, so I can easily calculate phi of N, or maybe not. If I can easily calculate phi of N, then I can easily find E, right? But the big thing about RSA is that if I have N and N is in fact a computation of two prime numbers, I cannot easily calculate phi of N. Okay, that's the big thing about the RSA. If I can find the factor, if I can factorize N, I can find P and Q, and boom, the problem is solved, because I can find phi of N and then I can find E. And that's why RSA is secure system. Okay, so you have P and K, and then we're gonna have F and F inverse this way. So x to the power of E is my F, y to the power of D is my F inverse. That's very simple. Okay, and then why this would work, I'll let you guys to kind of like go with this mathematical derivation of how this yd modulo n will result in x. This is the formula, and this is the reason. You will eventually will see that if I do y to the power of d, I'm gonna eventually get x. Okay, so this is your homework to kind of take a look at this. But basically, RSA is this very simple kind of like power of d, power of e. And that's all you need to have for encryption of the encryption. Okay. All right. So talk to you guys next time. We're gonna continue this.